Okay, so the second part of this projectile motion is going to deal with starting from a platform and shooting it. And so we're going to take exactly the same scenarios we had before, the 350 meters per second at 30 degrees for the projectile, but now we're going to start at 50 meters above the ground, or the ground level. And we're going to see how that has an effect upon how high from the ground is it going to reach and how far is it going to go. We're still going to look for two distances, but they're going to be different. So let's go ahead and take a look at that. And what we have here then, we now have a platform. And in the platform, you got the can being shot off at a 30-degree angle at 350 meters per second. So when we do the whole right triangle thing here, it's the exact same thing as what we had before. So to refresh your memory, we said that VV here was 175 meters per second. We said that VH is equal to 303 meters per second. Okay, so we're going to use those two values again. And what is different this time is we're starting at a height here of 50 meters. All right, and the other thing that's rather interesting here is that since all the calculations are the same here, if we pretend like this is the ground right here, if I just draw this across like this, then the time it takes to reach the apex, the height of the curve, will be the same as if we shot it from the ground. Because it's going to have the same effect on the VV that we had there, the 175 meters per second. And it's going to do this, but then the problem is it's going to go down past that. So this time right here, I'll call it time up, is going to be the same as the half time we had yesterday. And I believe that was 17.9 seconds. But you notice that this is no longer a symmetric curve. This is a curve in which it gets up there quickly, and then this part is going to be a little bit longer. How much longer? That's what we're going to have to calculate. How do we calculate that? We need to find out how high it gets. And then, since this is 50 meters, then the distance from here to here is going to be that height plus 50 meters. Now this is not drawn to scale, so this is not anything really exorbitant over here. But you know, trust me when I say it's going to be different. So to figure that part out. So here's how we're going to do that. We've already calculated this height here. I'll call this H1, and I'll put H top for this. H1, I'm sorry. I'll forget that whole top thing. I'll come back to that. H1 is what we calculated in the previous problem. We said that height reached, oh, I didn't put it there because I cheated, didn't I? We said that height was 1,570 meters. All right, so that was 1,570 meters. So this is H1 plus 50. So that's going to be equal to 1,570 meters plus 50 meters. So the total height is going to be 1,620 meters. So this is really a bad river. It goes way up there and then drops down here. So the bad drawing. It's shocking that I would come up with bad artwork. Who would have thought? Anywho. So now what we need to do is figure out the time it's going to take to start here and act as if we drop down. Leonardo not Leonardo da Vinci, Galileo performed this experiment from the Leaning Tower of Pisa, where they shot a cannon, and he dropped a cannonball at the same time it was shot to see which would land first, and it turned out that they both landed onto the ground at the same time. And so, what we're going to do here is we're going to find out the time it took to drop. If we just took the cannonball and was dropped right there, it's going to be the same as it's going to take to go all the way over here. So let's calculate that. So, the height we know is 1620 meters. And this is going to be equal to, and since this is going down, at this point the initial velocity is 0. So we don't have to do the VIT plus 1/2 AT squared, because the VI is 0, that drops that first part out. So this is 1/2 AT squared. So this is going to be 1620 equals 4 point, and that's G by the way, 4.90, because half of 9.80 is 4.90 T squared, divided by 4.90, and then take the square root of both sides. And T turned out to be 18.2 seconds. So this is 18.2 seconds. So that's T down. T up was 17.9, T down is 18.2 seconds, which kind of makes sense because that's way up in the air, and this is only like a drop compared to that. I mean, it's about 3%, if a little bit more than 3%. So the amount of time should be basically not very much, which is indeed the case. That means the total time is the sum of 17.9 and 18.2. T total equals 17.9 seconds plus 18.2 seconds, which is 36.1 seconds. So now we can calculate the distance, the horizontal distance, is equal to, and this is not accelerating, so this is just going to be V times T. And this is going to be velocity, we said was 303 meters per second, the horizontal. That didn't change. Time is 36.1 seconds. So the distance at which it travels, cheat time, drum roll, 10,900 meters. So it'll only gain an extra 100 meters being from that high. Okay? So we got some practice problems here, and I'm going to tell you right now about these practice problems. I'm intentionally trying to prove a point with these two and these two. So if you get an answer that for each pair of numbers for the distance traveled that seems kind of goofy, it's not. I guarantee it, unless you made some horrendous calculator mistake, which then goofy answer is what it is. But if you don't make the mistake, it's going to seem weird, but it's actually going to be correct, and then I'll explain it when we get a chance to get together and talk about this stuff. So have at it with this, and good luck.